Hello, in this particular session, let us discuss how the speed of DC motors can be controlled. So, in order to analyze the concept of speed control of DC motors, let us recall the speed current or the speed torque characteristics of DC shunt motors. So, here mainly we will concentrate on DC shunt motors. So if you recall the concepts of speed current characteristics, we can tell the speed regulation of DC shunt motors is very small, therefore it is good. And as the load on the motor is varied, the change in speed, if you observe, the change in speed is very small. That means at no load, if you assume the speed is n naught, that means n naught represents the no load speed of the motor. At full load, if you observe, the change in speed is very less, which is 1 or 2% you can observe. Therefore, the DC shunt motor is called as constant speed motor. So like this, based on the concepts what we have discussed in the previous sessions, we can move on to the speed control of DC motors. So here if you observe the equation 1, the back EMF is equal to 5Z NP divided by 60A. So EB is nothing but, as already we have seen, we know it is back EMF, that means the EMF whatever it is induced in the armature conductors, that is called as back EMF, which opposes the applied voltage, that one we have seen, where phi is the flux per pole, whatever the flux which is produced by the magnetic poles, that is represented by phi, and Z is the number of armature conductors which is placed in the armature slots, N is the speed of rotation of motor represented in RPM, P is the number of poles, A is number of parallel paths which is related to the way in which the winding is connected. The winding, the armature winding, the conductors which is placed in the armature slots, it is connected in the form of lap or wave winding. If it is lap winding, then number of parallel paths, that is the value of A is equal to 2 you can consider. A is equal to A is equal to P. If it is wave connected, if the armature conductors, if it is connected in the form of wave winding, therefore the number of parallel paths will take the value 2. A is equal to 2. So like this, the EMF equation has been derived in the previous sessions. So directly we have taken that equation in order to establish the relation, because what we need is the speed. That is, we need to control the speed of DC motor. So we need to vary some of the parameters in order to vary the speed. Therefore, we need to establish a relation between the speed and the parameters which we will vary. So for that, we need to take the help of some equations. So the second equation, if you observe the second equation, that is EB is equal to V minus IARA minus ARD minus BCD, where this is the equation which we got by applying KVL to the outer loop of the DC shunt motor circuit diagram. If you recall, the circuit diagram, that is, here you can observe this is the DC shunt motor. If you neglect this resistance, time being, it looks like supply voltage, field winding, and the armature circuit. Three things will be there in case of DC shunt motor: armature, field winding, and supply voltage. So if you apply KVL for this outer loop, if you observe for this outer loop, if I apply KVL, then I will get that particular equation, that is equation 2, where EB is equal to whatever the EMF which is induced is equal to V minus IRA minus ARD minus BCD. That means here if you observe ARD stands for armature reaction drop, BCD stands for brush contact drop. The armature resistance drop is due to the armature reaction, the effect of armature flux on the main flux takes place. Because of this, some amount of voltage drop takes place in the armature, that is called as armature reaction drop, what we can consider. The other one is the brush contact drop, the drop in voltage due to the brushes. The brushes actually it is made up of carbon. The job of brushes we have seen in the construction diagram, it collects the current and delivers to the load. In case of generators or construction diagram, while discussing, we have seen the brushes are made up of carbon, and the drop in the brushes, it is also very small. Because of drop in the brushes, some amount of voltage drops takes place in the armature, that is brush contact drop. So by comparing equation 1 and equation 2, we will get equation 3. That means we have neglected all the constant parameters in the equation, that is the number of conductors, poles, number of poles, the parallel paths. A represents parallel paths. We have neglected which are constants. We have neglected ARD and BCD. We have neglected, assuming the drop due to this is very small when compared to that of load current. We have neglected ARD and BCD. If you neglect the constant parameters and equate equation 1 and equation 2, you will get the speed is directly proportional to V minus IA RA minus IA RSC divided by 5. So if you observe the equation 3, the speed what we are trying to vary is directly proportional to V minus IARA minus IARSC. Here the RSC represents the resistance of series field winding, the resistance of series field winding, and IARSC represents the voltage drop in the series field winding. Here whenever we consider a DC series motor, at that time the IA RSC will come into the picture. Time being, we are concentrating on a DC shunt motor, therefore directly we can go for equation 4. The speed is directly proportional to V minus IARA divided by 5, what we can consider. That means the equation 4 you can consider. So here if you observe, by varying the flux, the denominator if you observe, that is the flux, by varying the flux the speed of the motor can be varied. What we can tell, by varying the IARA, that is the RA, the armature resistance, by varying the armature resistance, that means the resistance in the armature circuit, we can vary the speed. And the other parameter, the V, is nothing but the supply voltage. By varying the supply voltage, the speed of the motor can be controlled. Further, the equation actually it is simplified to N is directly proportional to V divided by 5. That means assuming the voltage drop due to the armature resistance is small, the armature resistance is very small when compared to load current, which is in terms of 0.1 or 0.2 ohms, less than 1 ohm. Therefore, the drop due to this is very small when compared to the load current. Therefore, what we can consider, the speed of the motor is directly proportional to V and inversely proportional to flux we can consider. So anyway, depending on the analysis, we can change the equations for the analysis, depending on the analysis. So based on these concepts, based on the equations, we can move and see what are the factors which affects the speed of a motor. That means we have standard equation we have taken, N is directly proportional to V minus IRA divided by 5. There is the standard equation which we have kept in order to control the speed of DC shunt motor. So by observing, we can tell the factors affecting the speed of DC shunt motor is, the first one is flux. What is flux? It is the magnetic field which is created by the poles, by the stationary part of a machine. So by varying that magnetic field or by varying the magnetic flux, I can change the speed. And the second parameter is the voltage across the armature. The voltage across the armature is nothing but VA. The numerator part, actually it represents the entire numerator part, I can consider as the voltage across the armature. V is the supply voltage minus drop across the armature results in a voltage across the armature. Or in the other way, by varying the armature resistance, by varying the resistance which is connected in the armature, I can control the speed of the motor. And the third parameter is the applied voltage. By varying the equations, if you observe, by varying this V represents the supply voltage, supply DC voltage. By varying this voltage, I can control the speed of a motor. So let us see how the speed of a DC motor is varied. The first method in the speed control is the field control method or the flux control method. As already we have seen from the speed equation, the flux, if it is varied, then automatically the speed of the motor can be varied. So let us analyze this. So if you observe the circuit diagram of a DC shunt motor, a resistance with a value of R has been placed in series with the field winding, Therefore, what we can tell, by varying this resistance, we are trying to vary the flux. By varying the value of resistance, we are trying to vary the value of flux. So here the remaining parameters, if you observe, it is as usual. We know that it is the supply voltage V which is given to the field winding and also parallel to the armature circuit. Whenever the voltage is given to the field winding, the current starts flowing through the windings. It creates the flux which is represented by phi. Phi is the flux which is produced per pole by single pole. Therefore, each and every pole will produce the flux. Therefore, a magnetic field has been created in the air gap. And whenever the voltage, again it comes across, whenever the voltage is applied to the armature current starts flowing through the armature conductors. Whenever the voltage is given to the armature circuit, the current, that is the armature current, starts flowing through the armature circuit. According to the principle of DC motor, whenever a current carrying conductor is placed in a magnetic field, it experiences a force. So each and every conductor which is placed in the armature slots experiences a forces. So all the forces collectively produces a torque, therefore the armature of the motor rotates. Therefore the armature of the motor rotates. So here the direction of rotation, it is given by Fleming's left hand rule. And what is the amount of torque produced? That one already we have seen from the equation 0.159 Z Ia into P by A. That one already we have discussed. In case of while discussing the characteristics, that is the torque current characteristics of different motors, we have seen whatever the torque which is produced by the armature is equal to 0.159 Z Ia into P by A. And the direction of torque produced or the force experienced by the conductor is given by Fleming's left hand rule. That one, all those things we have discussed previously. So here, what will happen whenever the voltage is given? We have seen how torque is produced and how the flux is produced by the field winding, how the magnetic field has been created. Now what he has done, he has placed a resistance in series with this, in series with the field winding. So now let us analyze by keeping the value of resistance 0. That means by placing this pointer at start position, what he has given at start position, So whenever the value of R is 0, you can observe the graph. That means the variation of speed here, if you observe, this one is a variation of speed without field rheostat, That means the value of R is 0. That means without including this resistance, how the variation of speed will be? It is like this. Without a resistance. So here this graph I will get the speed with field rheostat in the field circuit. Whenever we include some resistance, is included by varying this rheostat, at that time the graph looks like this. So here let us see the variation of speed with respect to load. Here in the y-axis, the speed has been taken, which is represented in RPM. In the x-axis, the armature current is taken, which is nothing but a variation of load. So what happens to the speed of a DC shunt motor when the load changes with different values of R? That one we have to see. So initially, let us start the analysis with R is equal to 0. That means the pointer at start position. So at that time when the voltage is applied, the current starts flowing through the armature and also through the shunt field winding, which produces a flux. Therefore, according to working principle, the motor starts rotating and torque is produced. So what about the speed of a motor? So at no load, if you observe, when the load is not applied, when the value of R is 0, I will repeat, when the here now I am analyzing with the value of R is equal to 0, load is not applied. When R is equal to 0, load is not applied. At that time, what is the speed of a motor which is equal to no load speed? I can consider this point. You can observe the pointer, no load speed of a motor when R is equal to 0 without field rheostat. It is here. So what happens as the motor is loaded? That one we have seen from the speed current characteristics. As the load on the motor varies, the current which is drawn from the supply and the current which is flowing through the armature conductors will vary. As the load is increased, Ia increases. As Ia increases, the IaRa drop increases. As IaRa drop increases, the V is constant. Then automatically the resultant of the numerator equation decreases. As the RHS of the equation decreases, numerator, then automatically the speed of the motor gradually decreases. You can observe. Initially at no load, the speed of the motor, if you observe, the speed of a motor is n naught, no load speed. As the load on the motor increases, the speed actually it is decreasing because of increase in IA. But the change in speed is very small because the value of RA is very small. Because the value of RA is very small, therefore the change in speed from no load to full load, it is very small. That means the speed regulation of the motor will be good. Speed regulation is good. Therefore, we analyzed the variation of speed with respect to load when the rheostat was placed at start position. That means the value of R when it is equal to 0, when the value of R is equal to 0, at that time we analyzed the variation of speed. Now let us change let us change the value of resistance to R1. Let us assume some value of resistance is placed. Let us change the value of R to R1, some value. This point only we can consider. The rheostat is placed in this particular position, some value of R is increased. At that time what will happen? Whenever the voltage is applied, again whatever the current which is flowing through the shunt field winding decreases. ISH decreases. As ISH decreases, because we have included a resistance, more value of resistance, the current will decrease. Therefore automatically whenever the current decreases, then automatically we know that whatever the flux which is produced by this field winding decreases. As this flux decreases, then automatically we know that whatever the flux which is produced is inversely proportional to speed, then automatically the speed of the motor increases, because it is inversely proportional to each other. Whenever the flux decreases, the speed of the motor increases. Therefore you can observe the graph. Earlier the speed of the motor with R is equal to 0 was here. Now the speed graph will start from this particular position, that is the speed is changed to N1. You can consider earlier it was N0, indicating no load speed of a motor at R is equal to 0. Now it is also no load of the motor, but after including the resistance, that is R is equal to R1, I can consider R is equal to R1. Some value of resistance has been included, therefore the speed curve has been shifted from this particular point to this particular point. That means what I can consider above rated speed. This is the rated speed, it has gone above the rated speed. Now what will happen? Now as usual, the load on the motor is varied. As the load on the motor is varied, the current drawn from the supply or the current drawn by the armature current increases. As IA increases, same IARA increases. As IARA increases, V minus IARA, what will happen? IARA increases, V minus IARA decreases. Because of this decrease, the speed is directly proportional to that. The speed of the motor decreases. You can observe. As the load on the motor is increased, because of increase in IARA increases. As IARA increases, the speed of the motor is reduced. So we will get this graph, the second graph. This is the variation of speed from no load to full load at some value of resistance, that is R1. You can take R is equal to R1. Here R is equal to 0. In the similar way, if you increase the value of R to R2, again include some value of resistance. Further, the current reduces, whatever the current which is flowing through the field winding reduces. As this current reduces, the flux decreases. As flux decreases, again the speed increases. Again the curve shift from this particular position to further higher value. Here you can assume this as N0 when R is equal to 0. At R is equal to R1, it is N is equal to N1. above rated speed. Again, when R is equal to R2, the speed will become N2. The graph again it starts from this particular position. As the load varies, again I will get another line like this. Another line I will get like this. So this is regarding the field control or the flux control method of DC shunt motor. Here, by including the resistance in series with the field winding, we can able to control the speed of a DC shunt motor. For that, we need to take the help of this equation, that is speed is directly proportional to V minus IRA and inversely proportional to the flux. So let us see the advantages of the flux control or the field control method. The first point, it provides relatively smooth and easy control. If you observe the circuit diagram, we have included only the resistance. So by varying the resistance easily, we can control the speed. Therefore, it is called as relatively smooth and easy control of speed can be possible with the help of flux control method. The second one, the speed control above rated speed is possible. That one we have seen, the speed control above rated speed. If you observe, this first point is the rated speed. This is the rated speed. Now what I will get, this is above rated speed. Whatever the speed I will get at this particular point, it is above rated speed. That means at R is equal to R1. Further, again if I include another resistance, still more resistance, I will get further higher value of speed. Therefore, what I can tell, by field control method or flux control method, the speed can be varied above rated value. The speed control above rated speed is possible. The third point, if you observe, as field winding resistance is high, as field winding resistance is high, that means he is talking about RSH. RSH in the circuit, if you observe the RSH, it is the resistance of the shunt field winding. He is talking about this particular value. As field winding resistance is high, the field current is small. Okay. Hence, the power loss in the external resistance is very small, which makes the method more economical and efficient. That means, as the value of this resistance is high, whatever the current which is flowing through this path is very less. The drop or power loss due to this is talking about the power loss. That means ISH is the current which is flowing through this. The loss due to which is nothing but ISH square R loss. The loss in this resistance is ISH square R loss. It is very less because ISH is less. Therefore, this method is more economical and efficient one. Whenever the losses is less, then automatically the efficiency of the machine or the system will be good. The fourth point, as the field current is small, the size of the rheostat required is small. So as the field current, the current which is flowing through the field winding is very less. Therefore, whatever the rheostat which we need to place in the field winding in order to control the flux, in order to control the speed by varying the flux, that is talking about the size of the rheostat required is less. The size of the rheostat required is less. So this is regarding the advantages of flux control or the field control method. Let us see the disadvantages. The first point if you observe, the speed control below rated speed is not possible. That means if you observe the graph, that is above rated speed, this is the point rated speed, above rated speed we are getting the graph, but we cannot control the speed of the motor below the rated speed, that is the disadvantage of first one. So as the flux reduces, that means Why the flux will reduce? Because of increase in the value of rheostat. As the value of rheostat increases, the flux production reduces, the speed increases. That one we have seen how the speed will increase. But high speed, high speed is nothing but is talking about in the graph we have seen N0, N1, N2 represents the higher values of speed, above rated speed. N0 represents the rated value of speed. N1 above rated speed. N0 is less than N1 is less than N2, or in the other way N2 is greater than N1, N1 is greater than N0. Like that, the higher speed, but higher speed affects the commutation, making motor operation unstable. Higher speed affects the commutation, making motor operation unstable. That means as the speed of the motor is increased, then the motor will not operate in a stable condition. That means the characteristics is talking about the characteristics what the motor exhibits at higher values of speed will be undesirable, will be impractical. Therefore, that one we can call as unstable operation region of the motors. Therefore, there is a limit to the maximum speed above the normal value. There is a limit. We cannot increase directly the value of resistance, that means the rheostat, to any value. There is a limit to a maximum speed above the normal value. Normal value. So this is the disadvantage of the flux control or the field control method. So based on these ideas, we can go for MCQs. So here if you observe the first one, the speed of the DC motor depends upon, already we have seen the speed of the motor, it depends on the factors which affects the speed. We have seen that is it affects the parameters, the flux, the voltage across the armature and the applied voltage. That is clear from the equation. Therefore if you observe flux per pole, the first one is flux per pole, applied voltage to the armature, the voltage drop in the armature circuit resistance, and all of the above. You can go for the option all of the above, because as we know that from the equation N is directly proportional to V minus IRA. Therefore V, the supply voltage will come into the picture. V, by varying V, the speed can be controlled. By varying the armature resistance, the speed can be controlled. By varying the flux, also the speed can be controlled. Therefore, by varying all the three parameters, the speed of the motor can be varied. Therefore, you can go for option D. Then the second one, the speed of a DC shunt motor may be varied by varying field current, the supply voltage and the armature circuit. So here the option is, the answer is the A and B you can consider. It is not C, it is A and B. By varying field current, that means the shunt field current, we can vary the flux, therefore the speed can be controlled, and by varying the supply voltage also we can control the speed of a motor. Here by varying armature circuit he has given, if he has given armature circuit resistance, then we can consider the equation C, but here he has not given equation C, he has not given the resistance, he has given just a armature circuit. He has to tell the parameter what you are varying, therefore we can neglect C, you can go for option A and B. It is not C, it is answer is A and B. That means by varying field current and also by varying supply voltage, I can vary the speed of a DC shunt motor. The field flux method of speed control, DC shunt motor is generally used for which of the following? Here, if you observe, it is constant HP drive below the base speed, Base speed is nothing but the rated speed what we can consider. Constant torque applications above rated speed, constant torque applications above the base speed, constant HP applications above base speed. Here you can consider, we have seen from the graph, the speed is controlled above the rated speed, above the base speed. Therefore, we can go for option D. That is constant HP drive above the base speed, above the rated speed what we can consider. The fourth question, a DC shunt motor is fitted with a field regulator for speed control. For a constant load torque, the speed will be minimum for a regulator resistance of. For a regulator resistance of. That means a DC shunt motor is fitted with a field regulator for a speed control. That means he is talking about field regulator is nothing but a resistance which he has placed in the field circuit. For constant load applications, the speed, when the speed will be minimum, he is talking about speed will be minimum for the value of resistance, for the value of resistance. So, at what value of R, the speed of the motor is minimum, is telling minimum. Here you can go for the graph. Here if you observe, for R is equal to 0, it is N0. For R is equal to R1, it is N1. Further, if I increase R is equal to R2, again I will get higher value of N2. Therefore, at what value of R the speed is minimum, I can tell at R is equal to 0. At R is equal to 0. Therefore, the answer you can consider at R is equal to 0. Therefore, the option B. At value of R is equal to 0, the regulator resistance, whenever it is 0, the speed will be minimum we can consider. Which of the following statements associated with the field control of DC shunt motor is correct? So here, if you observe, he is telling the option C, the speed can be varied above to the extent of satisfactory commutation and below no variation. That means the speed can be varied above the rated speed to the extent of satisfactory commutation. Below the rated speed, we are not varying the speed of the motor. That means we can go for the option C, because the speed control above the rated speed is possible, below the rated speed is not possible. Therefore, you can go for option C. A DC shunt motor is supplying a load at its rated speed. The speed can be reduced. The speed can be reduced by, he has given different techniques, that is the armature circuit resistance, field resistance control, Leonardo speed control methods, and any of the above. Here you can go for the option A. A DC shunt motor is supplying a load at its rated speed. The speed can be reduced by the armature circuit resistance control, you can consider. The seventh question, if you observe, the resistance of the field regulator of a DC shunt motor is order of, what is the value of resistance which we will place in the field control method? It is generally, you can consider it is 100 ohms. It is 100 ohms. The eighth question, a DC shunt motor is fitted with a field regulator for speed control for constant load, for constant torque load, the speed will be minimum for a regulator resistance of dash ohms. So here, when at what value of resistance the speed will be minimum? Already we have seen in the previous, when the value of resistance is 0, at that time the value of speed will become minimum. The speed will be minimum. Therefore, the ninth question, a variable resistance in series with the shunt field winding in a DC machine is called as dash field regulator. Already we have come across the term field regulator. You can observe the field regulator, whenever the resistance comes in series with the field winding, therefore I can call that one as a field regulator. In DC motors, the field control method is used to have speeds dash rated one, that means above the rated one, above the rated one, because below rated one is not possible. In case of field control method, we can consider the speed above the rated value, therefore above rated values. The next question, the speed variation of a DC shunt motor by the field flux control method or the flux control method or the field control method is suitable for dash drives. Here we can take for power drives. Can go for power drives. So in this particular session, we have seen how the speed of a DC shunt motor can be varied by varying different parameters, that is by varying flux, by varying voltage, and by varying the armature circuit resistance. We can vary the speed of a DC shunt motor. And also we have seen in detail about the flux control method or the field control method of DC shunt motor. Thank you.